Here's the text with punctuation added. Something is amiss in our comprehension of the universe. Cosmology is, by all accounts, heading for a confrontation on one of its most fundamental inquiries. How quickly is the universe expanding? For more than a decade, two kinds of estimations have been in conflict. Perceptions of the current universe ordinarily find the rate of development, called the Hubble constant, to be around 9% quicker than expectations based on early universe data. Specialists trusted that the James Webb Space Telescope, the most exceptional telescope ever assembled, would assist with settling the inquiry once and for all. However, agreement has thus far failed to emerge. Instead, the Space Observatory has established the disparity with incredibly exact, groundbreaking observations that threaten to overturn the standard model of cosmology. The new physics expected to change or even supplant the 40-year-old hypothesis is now a subject of debate. A thrilling and fascinating possibility is that there's something we fail to comprehend about the universe. Join us as we dive deep into how new ultra-deep pictures from James Webb have confirmed that there is something genuinely amiss with our understanding of the universe. Our universe began with a bang. The enormous detonation, energy, mass, and space streaked into reality all within a transient moment. Then, the youthful universe was formed. A growing, roiling plasma stock of matter and antimatter particles that sprang into reality just to destroy each other upon contact. Left to their own devices, the matter and antimatter inside this plasma ought to have consumed each other completely. However, researchers believe that some unexplored cosmic imbalance allowed more matter than antimatter to be produced, saving the universe from immediate implosion. Gravity packed the plasma pockets, crushing and warming the matter so that sound waves traveling just over around 50% of the speed of light, called baryon acoustic oscillations, undulated across their surface. In the meantime, the high energy density of the early universe's packed contents expanded spacetime, pulling a small part of this matter securely from the fray. As the universe expanded like an inflatable, the standard story goes that ordinary matter, which interacts with light, coagulated around clusters of invisible dark matter to form the first galaxies, connected together by a vast cosmic web. At first, as the universe's substance spread out, its energy density and thus its expansion rate diminished. However, about 5 billion years ago, galaxies began to retreat once more at an ever-increasing rate. The reason was another invisible and baffling substance known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the expanding fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our universe expanded, its overall matter density dropped while the dark energy density remained the same, gradually making the latter the greatest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda cold dark matter, lambda CDM model of cosmology, which maps the expansion of the universe and predicts its end, with matter eventually spreading so far that it encounters an intense demise called the Big Freeze. Many of the model's predictions have been shown to be highly accurate, yet here's where the problems begin. Despite much searching, astronomers do not know what dark matter or dark energy are. As Ofer Lahav, a professor of cosmology at University College London, who is involved in systematic studies of dark energy, said, "The majority agree that the universe's current composition is 5% ordinary baryonic matter, 25% cold dark matter, and 70% dark energy. The embarrassing truth is we don't understand the latter two yet. An even greater threat to the lambda CDM model has emerged. Depending on what technique astrophysicists use, the universe appears to be expanding at different rates, a discrepancy known as the Hubble tension. Methods that probe into the early universe show it expanding significantly faster than lambda CDM predicts. Those methods have been checked and confirmed by numerous observations. Accordingly, Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurement, said, "The only reason I can understand at this point for them to differ is simply that the model we have between them is perhaps missing something. Measuring the universe's expansion takes more than a radar gun. The primary method to measure this expansion looks at the so-called cosmic microwave background, CMB, a remnant of the universe's first light emitted only 380,000 years after the Big Bang. The imprint can be seen across the entire sky and was intended to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this astronomical baby picture, the universe is largely uniform, yet hotter and colder patches, where matter is more or less dense, reveal where baryon acoustic oscillations made it cluster as the universe exploded outward. This soap bubble structure expanded into the enormous web, an array of tangled strands along whose intersections galaxies would form. By studying these waves with the Planck satellite, cosmologists inferred the amounts of ordinary matter and dark matter and a value for the cosmological constant or dark energy, resulting in a Hubble constant of about 67 kilometers per second per megaparsec. Let's pause on this number for a moment. If a galaxy is a distance of 1 megaparsec away from us, that would mean it is receding from us and we from it at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second and continues to increase dramatically from there. If a galaxy is any farther than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables, dying stars with helium gas outer layers that expand and contract as they absorb and emit the star's radiation, causing them to periodically twinkle like distant signal lights. In 1912, astronomer Henrietta Swan Leavitt discovered that the brighter a Cepheid was, the slower it would twinkle, enabling astronomers to measure a star's absolute brightness and thus measure its distance. It was a landmark discovery that turned Cepheids into plentiful standard candles to measure the universe's large scale. By combining observations of Cepheids, astronomers can build astronomical distance ladders, with each rung taking them a step further back in time. It is perhaps one of the most accurate means that cosmologists have today for measuring distances. To build a distance ladder, astronomers start with nearby Cepheids and cross-check their distance based on pulsating light against that found by methods such as those used by Wendy Friedman, an astrophysicist at the University of Chicago. The next rungs are added using Cepheid readings alone. Astronomers then look at the distances of stars and supernovae on each rung and examine how much their light has been redshifted, stretched to longer, redder wavelengths as the universe expands. This gives an accurate measurement of the Hubble constant. In 2019, the method was used by Rees and his colleagues, who pointed the Hubble Space Telescope at one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was striking, an incredibly high expansion rate of 74 kilometers per second per megaparsec compared to the Planck measurement. However, Hubble lacked the necessary accuracy for the dense regions of space the team was studying, causing some distant Cepheids to blend into neighboring stars. Thus, cosmologists had some room to argue that the result, though surprising, might have stemmed from a measurement error. When James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 6.5 meters wide, Webb's mirror is more than twice the size of Hubble's, which is only 2.4 meters wide. Not only can James Webb detect objects 10 times fainter than Hubble, but it is also significantly more sensitive in the infrared range, allowing it to see a wider range of wavelengths. By comparing Cepheids measured by James Webb in the galaxy NGC 4258 with Type Ia supernovae, a different standard candle since they all explode at the same absolute brightness, in distant galaxies, Rees and his colleagues arrived at an almost identical result, 73 kilometers per second per megaparsec. Other measurements, including one made by Friedman with the Hubble Space Telescope on the rapid fading of the most luminous tip of the red giant stars, and another with light bent by the gravity of massive galaxies, returned values of 69.6 and 66.6 kilometers per second per megaparsec. A separate result using gravitational lensing also gave a value of 73 kilometers per second per megaparsec. Cosmologists were left reeling. According to Ranjan Kai, a cosmologist at the University of California, Merced, who has been working to understand the Hubble tension, the CMB temperature is measured to an accuracy of 1%, and the Cepheid distance ladder is approaching 1%. So, a difference of 7 kilometers per second, although it's not enormous, is extremely unlikely to be a random chance. There is a clear need to make sense of this. The new outcome leaves the answer wide open. splitting cosmology into groups pursuing vastly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 meeting at the Kavli Institute for Theoretical Physics, KITP, in California only led to more frustration. As the late Vera Rubin, who found evidence for dark matter, said at the time, "No one wanted to give up their toy. Each individual